Hey y'all! So a thing happened. Hi everybody, and welcome to this week's episode of this show. So I thought I would go over some things. The other day I was doing some lessons on the computer on actually how to make these videos, how to do a better job of making these videos, and I noticed that I had a malfunction in the computer. Not the computer specifically, but the cooling solution that I have for the computer. I actually have a refrigeration compressor and circuitry cooling the computer through the oil. A lot of you guys out there will recognize, oh, it's an oil submerged computer. Like, that hasn't been done a million times. Well, obviously. But what I haven't seen is somebody actually chill the oil that cools the computer, which is what this is doing. Now, I'm not 100% happy with this particular setup. It's actually pretty old. It's the very first version that I tried, and it has bugs. Definitely things that I want to improve on the next version, which is part of the project, the big project that I eventually want to build. So I guess that's kind of a sneak peek of some of the things I want to do in the future here. But I thought, since this thing had a malfunction, we might as well walk through finding out what that malfunction is and see if we can't fix it. So that being said, let's get started. Now, the first thing I want to do is talk about the principles that actually allow this to work. This refrigeration system is built on what's called a state change or phase change cooling technology. It's more of a principle than a technology. It's very widely used, but refrigeration in general uses state change or phase change science to function more efficiently. Now, what this means is, take water, for example. If I take a pot of water and I put it on the stove, and then I turn the stove on and heat that water up, that water eventually gets to boiling, and then it turns to steam. Well, the act of turning from water to steam is called a state change or phase change. The act of that happening involves a lot of science in the realm of energy and in the form of heat to accomplish that change. We use that science to more efficiently cool down products such as your grocery stores and all your walk-in freezers or the reach-in freezers, the coolers, your air conditioning. This has been done for a long time, literally over 100 years. They've been using this kind of technology to cool things, even to something as simple as swamp coolers, where they literally just run water over a bunch of grates and blow air through it and it cools the air off. That's still a state change technology, because the heat from the air is causing the water on a small scale to boil and evaporate. Not necessarily boil, but it's causing it to evaporate, and as it evaporates, it takes with it latent heat, making the air cooler. That's super generic. There's a lot more involved in that, but that's basically the idea. So let's go over what makes the refrigerant system work. And then once we do that, then we'll go into depth on why this system in particular isn't actually working. So I got a whiteboard. We're going to try drawing this out to help you guys follow along better, and we're going to explain how the refrigerant cycle works. Okay, so let's get started with some basics of refrigeration or air conditioning. Now, first thing I want to do is lay out some points, 3 points to be exact, so that I can describe this basic function to you clearly. The first of which, the entire point of air conditioning or refrigeration is to heat or cool an object. That means we are taking heat from one substance and moving it to another. In the case of air conditioning, we are taking heat from inside a house and moving it to outside the house. Therefore, heat is what we are interested in. So we are going to define heat and say how it's measured. So heat, point number 1, heat is measured in British thermal units, otherwise known as BTUs. Now, traditionally, BTUs are defined as the amount of heat it takes to raise 1 pound of water 1 degree. So that's 1 pound of water, not a gallon, 1 pound of water 1 degree. So if I take a pound of water and I move it from 60 degrees to 61 degrees, I have added 1 BTU. Number 2, the point of BTUs, or how we are going to accomplish our job. So point number 2, BTUs are moved by creating a difference pardon my my drawing here. I'm sure it's pretty rough. By creating a difference in between two elements. And spelling's probably horrible as well. Either way, you get the point. Now, we are moving BTUs by creating a difference. That means if I want to heat a space, I need to put hotter air into that space than is already there. Otherwise, I'm not accomplishing anything. There's a difference. That's how we make it happen. This is really the nuts and bolts of how this works in the first place. The third point, and the most critical point, is you can't compress a liquid. And you may be thinking to yourself, if you're not familiar with refrigeration, you may be thinking to yourself, why in the world do we care that we can't compress a liquid? Well, we are dealing with mechanical cooling. And mechanical cooling uses a compressor, normally uses a compressor to drive the entire process. And compressors, you can't compress a liquid. So the absolute most important thing to making sure the system stays working is that the compressor never sees a liquid. Now that's important in more than one way, but you'll see why and you'll see how in just a moment. So those are your 3 points. You can pause and then write them down, because that applies, those 3 points apply to any air conditioning or cooling system you're working on. So let's start by drawing a diagram of the refrigeration process. Now we're going to start with the compressor. It's known as the heart of the system. The compressor provides the motion. It's what gets everything moving. Without the compressor, everything just kind of sits there and does nothing. So we need the compressor to move the gases and fluids along. So compressor. It's kind of like your heart in your body. It moves the blood. Alright, now from the compressor, we go to a condenser. Usually, the most common form of condenser is an air-over refrigerant condenser. That means that we have pipes that carry the refrigerant inside the condenser, and those pipes are being cooled or blowed on by air over refrigerant. From the condenser, we go to a regulator. This is commonly drawn in the form of an X because there are several different kinds of regulators. So this has a very, very important job, but its primary function is to change a pressure difference to accommodate what we're trying to accomplish. From the regulator, this is usually a very short trip, we move to an evaporator. Again, this is most commonly an air over refrigerant coil. So copper pipes carrying the refrigerant, and we blow air across it. We then go back to the compressor. Like I said, very basic system. We're going to label these out. So condenser, regulator, and evaporator. For basic components. Now, most systems have a lot more than this. Your average window unit pretty much sticks with this, with these 4 components. But it's always at least these 4 components. So let's start the refrigerant process. We're going to start at the compressor. We are exiting the compressor as a high pressure, high temperature gas. Now it's important to note that that is a gas. Like I said, the compressor can't actually pump liquid, can't compress liquid. So high temp, high pressure gas. The reason this has to be high temperature and high pressure, the reason we have to use a compressor in the refrigeration world as it is normally consisted of is because, again, we need that temperature difference. We are normally cooling the condenser with outside air. That big old unit you got sitting outside your house, that's the condenser. Because we're normally cooling the condenser with outside air, that can get as warm as 90 degrees or 100 degrees, or slightly more in some extreme situations. Which means if all I do is put 80 degrees of fluid into this, or 80 degrees of vapor into this, then it doesn't actually cool down. In fact, we would be warming up the gas, and that would be defeating the purpose. So we drive the pressure up, because that also drives the temperature up. We drive the temperature over the existing outside temperature. To keep things simple, we'll just say that if we set our temperature of the condenser at 120 degrees, which means, let's just, for shits and giggles, let's just say that to be 120 degrees, we need to be 250 psi, will get us 120 degrees in the coil, then that means that it's never going to be 120 degrees outside. So we're always hotter in the coil than we are outside. And that drives your BTUs from the coil to the outside air. Now, the critical function of the condenser, the reason we need to cool down the refrigerant, is because of a special thing called the state change or phase change. We're a gas, and we're entering as a gas. And then at some point, we are removing enough BTUs to condense and turn into a liquid. That's our critical point. That's where we change states. That's where we change phases, and that's where this entire system works. That's the magic in refrigeration and air conditioning as we know it in modern days. So we have removed enough BTUs from this gas to condense it to a liquid. So we're coming out of the condenser as a liquid. Now mind you, in order to compress a substance, we need to push it against a restriction. In this case, the restriction is the regulator. So we are pushing all of this against the regulator, which means this is still high pressure liquid. But the temperature has dropped, obviously. So we're just going to say that at this point it's a high pressure liquid. That's our important part right there. High pressure liquid. Now the regulator has a very special function. It does two things. For one, it drops the pressure. Because this is still warm and a liquid line, which is what this is called, is normally between 90 and 110 degrees on a standard air-cooled condensing system. That's high temperature, medium temperature. Low temperature can be a little different, and in specialty cooling it can be a lot different. But normally what you're going to run into is a liquid line of between 90 to 110 degrees. That's not going to cool the environment. That's not going to cool a house, and it sure as shit isn't going to cool the product in a grocery store. So we need to drop the temperature. Well, materials, matter, especially refrigerant, has this cool thing where if you drop the pressure, the temperature goes with it. If you raise the pressure, the temperature goes with it. So the regulator's primary function is to drop the pressure from a high pressure to a low pressure. And in turn, it goes from a low pressure to a low, it goes from a high temperature to a low temperature. But it's still a liquid. Now, we're actually glad that it's a liquid, because in the liquid form, we have much higher molecular density, or at least material density, in order to do the job that it needs to do, which means we need less liquid to do the same job. So we're coming out here as a low pressure, low temperature liquid. We then enter the evaporator. In the evaporator, this thing's job is to add heat to that liquid. Again, normally this is an air over refrigerant cooling device. So it's a coil. We blow air across it, and relatively speaking, it's warm air across it to get cold air from it. So we're entering as a liquid, and we're going through most of the coil as a liquid until just towards the end, when we added enough BTUs to turn it into a vapor. This is where the magic happens. Again, we are changing states. We are changing phase. We are changing from a liquid to a vapor. Now, it is very important to change to a vapor because, again, the compressor doesn't compress liquid, it compresses vapor. So it's very important that has to be a vapor. But it is also very important to have added enough heat to this liquid to turn it to a vapor. That's how we know that we have removed enough BTUs from this space to actually do its job. So we come out of the evaporator as a low temp, low pressure vapor, or gas. I guess we use gas over there, so gas. Again, the states of the refrigerant are important because this needs to see gas and this needs liquid to be efficient. So, if this is so important, how do I make sure it's actually happening? I can't see inside the copper lines to actually see the refrigerant and what it's doing. Is it a liquid in there? Is it a liquid in here? Am I seeing liquid back to the compressor? I don't know. So here's what we do know. We can use numbers and testing equipment to find out. In the case of a condenser, we are removing heat from the refrigerant. A condenser removes heat from the refrigerant. And in order to know that we've actually removed enough heat, we use a number called subcooling. Now, yes, I said a number. That usually comes in the form of a number. I can say I have 10 degrees of subcooling. Now, subcooling by definition is the amount of heat I remove from the substance after it already condensed. So it changed from a gas to a liquid. I continued to remove heat from that liquid. The amount of heat that I continued to remove from that liquid is known as the subcooling. Now, the amount of subcooling isn't critical. It's the fact that we have subcooling. That's the critical point. The same thing can be said with the evaporator. How do we know that it has changed to a gas? In the evaporator, we're adding BTUs, or we're adding heat. We have a number called superheat. Superheat, by definition, is the amount of BTUs that you add to a liquid or to a substance after it has already evaporated. So it changed from a liquid to a gas. We added temperature, we added BTUs, we added BTUs. It changed to a gas. We added some more BTUs, we added some more BTUs. Those extra BTUs are known as the superheat. So I could say I have 20 degrees of superheat. That means I added 20 degrees after it already evaporated. Now, these numbers are achieved by taking pressures and taking temperatures and calculations in order to prove those numbers. But all you need to know is that that is how we prove that this is indeed a liquid and this coil is working, and that this is indeed a gas and that this coil is working. This number is very important to make sure the compressor doesn't go boom, and this number is very important to make sure the system actually does what it's supposed to. So that is a basic refrigeration system. Hi everybody. So putting this to some more practical use. So you've learned about the principle of how the refrigeration system works. Hopefully you've understood it at least enough to know what I'm talking about here. But what I actually have a problem with in this instance is my compressor is not running. I can hear it, it makes a tone, but it is not actually producing the pumping action or the compression action. So we're going to try diagnosing that. I'm predicting it's a locked rotor, but we're going to make a couple tests to see specifically is it or is it not salvageable. So bear with me, and I'm going to try doing this whilst holding it by hand, so this may be shaky. But bear with me, we'll see how this works out. So we have here the basic system. On the left side, you can easily see the compressor, which makes the whole system work. In the middle of all this is the circulator pump, which is moving the oil from the tank. It sucks it up right through that brass fitting you see up there. It sucks the oil up, pulls it down here, pumps it across and into a flat plate heat exchanger that you can kind of see up there. From the flat plate heat exchanger, then it goes back down and dumps it back into the tank. Precisely right there. Here you have the start capacitor for both the condenser fan motor as well as the compressor, or I should say the run capacitor. and the Dixel controller that takes care of turning everything on thermostatically. So that has a temperature sensor that reads the temperature of the case. I believe that's right there. You can see it on the green line. And it takes that information and then tells the compressor whether it needs to turn on or off. Below that you have several switches. This switch turns on the circulator. This switch disables the compressor. So I can turn the compressor on and off depending on how I desire. So what I have here is an instance of the compressor is not running. Now the first test we're going to perform right now is I have my amp clamp set up here to read the amperage of the compressor and what it's drawing. I have the controller here making sure that it is actually calling for the compressor, indicated by that there snowflake. And I have my multimeter set to volts. So what we're going to do is turn the compressor on, see what amperage it's drawing, and then make sure that it's drawing the correct voltage. So let's see how this goes. So that's 19 amps. And then I should be able to read from there. Oh, compressor just tripped out on thermal overload. But let's make sure that it's actually getting the voltage it's supposed to get. So I go from neutral on my terminal strip to compressor. From there, and 120 volts. Now I can tell you, because I already looked up the specs on this thing, locked rotor amperage for this compressor is 20 amps, which means it's going to draw 20 amps if the rotor is locked up and not spinning. And you can see there we're at 18 amps, and then it kicks back off again. Now the second test I need to perform to ensure that this compressor is indeed locked rotor is this here run capacitor. If this here run capacitor is not correct and it feeds the wrong voltage / amperage or the wrong wattage to that compressor, it again will not turn over correctly. So I've got my multimeter here set to microfarads, and I have the, you'll notice I have the lead disconnected for hermetic. Now this is also a 35 plus 6 dual capacitor. So that means I got 35 microfarads for the compressor and 6 microfarads for the condenser fan motor. So we're going to test the hermetic side, which should be 35 microfarads. And if I read on the meter, indeed, it is reading 35 microfarads. Now what this tells us is that the compressor is indeed locked rotor. In other words, it is mechanically jammed, and no matter how hard the motor tries to turn it, it just won't. Now normally that pretty much condemns a compressor, as in you need to replace it. Now I'm going to try one trick of relieving the pressure on the compressor and seeing if that doesn't help, but I'm really predicting that that's not going to do anything for us here. So we gave it a good old effort. I did drop the pressure in the system. Compressor's still locked up. So that thing is definitely internally foobarred. That being said, I do have a repair in mind. I do have the things I need to get it together for the most part, but we're going to make that a separate video, repairing the refrigerant system in this so that we can continue using the computer as it was designed to be used inside the oil. So thank you guys for watching. That concludes this video in this series. Stay tuned for the repairs and other projects to come. Y'all take care now.